In this class, we will discuss about one important principle called D'Alembert's principle, developed by D'Alembert, which explains how to analyze a problem when a body is in dynamic equilibrium. So we have learned about static equilibrium conditions whenever a body is at rest and it is subjected to a system of forces. Three equilibrium equations we are going to use for analyzing static equilibrium problems in non-concurrent force systems. They are sigma fx0, sigma fy0 and sigma m0. Whereas for concurrent force system we use only two equations of equilibrium, sigma fx0 and sigma fy0. In the case of dynamic equilibrium, the difference is whenever a body is moving, there will be a force which opposes the motion, which is called as the inertia force. Inertia force mainly depends on the mass of the body and also acceleration of the body. We know according to Newton's second law, F is equal to m into A. According to that, if you multiply the mass of the body by the acceleration, whatever force you are going to get, that is known as the inertia force, which tries to keep the body in position, whether it may be at rest or uniform motion, unless it is disturbed by another external agent or another force. So that means in the case of dynamic equilibrium, we are going to have an additional force called inertia force, which should be considered in solving the problem, which is m into A, which acts in the opposite direction of the direction of motion, just like frictional force. So inertia force and frictional force always act in the direction opposite to the direction of motion, and using that we can now come to the explanation of D'Alembert's principle. So I will consider an object like this or a body which is subjected to number of forces F1, F2, F3. So due to the effect of those forces, we can always have a resultant single force which has the combined effect of all the individual forces. The direction of motion will be there along the direction of the resultant. Let us say this body is moving in this direction because the resultant I have taken like this. And as I already told, this inertia force m into A, Fi, is the inertia force, will be acting in the direction opposite to the direction of motion like this. So here I have taken R as the resultant force of all these individual forces. Fi is m into A, which is the inertia force, which will be in newtons, both of them. M is the mass of the body, SI unit is kgs. W is the weight of the body, it is in newtons. A is the acceleration of the body in meter per second square. Now, whenever a body is subjected to number of forces, we can always find the single force resultant by using the equations, whether it is concurrent force system or non-concurrent force system. Once you get that resultant force, you can write the dynamic equilibrium equation. So as I already told, inertia force acts in the direction opposite to the direction of the motion of the body. That inertia force is m into A. That you have to keep in mind. Now what is dynamic equilibrium equation? Just like static equilibrium equation, you have the dynamic equilibrium equation like this. Vector R minus m into vector A is equal to 0 vector or null vector. That means I have written the vector form. R is the resultant vector, m is the mass of the body, which is a scalar, A is the acceleration vector, and RHS will be a null vector. Or in scalar form, if you write, it is equal to R minus m A is equal to 0. This is the scalar form of the dynamic equilibrium equation. This is the vectorial form. Now, according to the D'Alembert's principle, the statement runs like this: the system of forces acting on a body like this, F1, F2, F3, F4, in motion is in dynamic equilibrium. It will be in dynamic equilibrium because it is in motion with the inertia force of the body. So, whenever you talk of dynamic equilibrium, inertia force is a must. We have to consider the inertia force which acts in the opposite direction of the direction of motion of the body. So, if you take the resultant force as R, inertia force as m into A, so naturally this entire thing, all these forces will be replaced by this R acting in this direction, which should be equal, opposite and collinear to this inertia force. then only the body will be in equilibrium. That is why we write it as R minus Vma. This R consists of so many forces. Now this is an example which I have taken. So you can see here there is an object or a body having weight W. I am going to apply a force P in this direction. The tendency of the block is to move towards right, that is in the direction of the applied force P. Naturally, the inertial force acts in the opposite direction, like this. Fy is equal to m into a, where m is given by w by g. So w is equal to m into g. That is the relationship between mass and weight. Once you have the weight of the body, you can find out the mass just by dividing it by 9.81 meter per second square. That is acceleration due to gravity. Now, what I am going to do, this is the dynamic equilibrium problem. I am going to apply the two equilibrium equations. If you apply static equilibrium equation, it will be like this: sigma Fy0, sigma Fx0. As usual, using sign convention towards right positive, upward positive. If you apply, it will be W minus n minus W is equal to 0. So W is equal to n. That is the vertical forces equation. Horizontal force equation is in the direction of motion. P is positive, Ma is negative. F is a friction force here. Treating this surface as a rough surface, there will be frictional force acting in the opposite direction of motion, including the normal reaction. The relationship between frictional force and normal reaction is F is equal to mu into n, where n is the normal reaction, mu is the coefficient of friction. All this you have learned in the friction chapter. So these two are the equilibrium equations. Among these two, this itself is the dynamic equilibrium equation, which you can write it as R minus Ma is equal to 0, where R is P minus F. You can see here what is the resultant force acting in this direction, P minus F. So that will be equal to this Ma. So that is why either you can write like this or like this. Anyway, one thing you have to keep it in mind, that when you are writing D'Alembert principle, acceleration term should be there. Inertia force, you have to consider m into a. So whatever forces are acting in the direction of motion, that is your R, resultant R. And minus Ma represents the inertia force acting in the opposite direction of R. So if you write, so this is your D'Alembert principle equation. Now they will ask what are the applications. So applications of D'Alembert principle. So here the thing is, dynamic problem can be converted to a static equilibrium problem. So that's what I told you. So either you can use this equation or you can use this equation. Both are same. So this dynamic equilibrium equation problem can be converted to static equilibrium equation problem. Structural dynamics problems can be analyzed. So this is another important branch of civil engineering, structural engineering. Whenever an object is subjected to dynamic loads, for example, earthquake load is a dynamic load. So whenever it is subject, suppose I have taken a simple frame here, two-dimensional frame, subjected to some loads like this. So these are static loads. So static loads, whereas earthquake force which acts in the at the basement, at the base of the structure, is a dynamic force. This is a dynamic force. Earthquake force is a dynamic force. Whenever it is subjected to dynamic loads, then inertia force will be acting in the opposite direction of motion. So this building will it may start vibrating in this direction. Of course, that vibration will be very small. Deflection will be very small. So if the intensity of that earthquake load is very high, then there will be high deformations and the structure may collapse. So inertia force acts in the opposite direction. So such types of problems, if you write the forces acting in the direction of motion, minus m into a is equal to 0, you can solve for the unknown thing. Next, the generalized Newton's second law of motion, you know that it is F is equal to ma, is a generalized Newton's second law of motion that we have learned. Here if you replace this F by R, F is replaced by R, and what happens here? R is equal to vector R is equal to m into vector A, or R minus ma is equal to 0. That means you can say that Newton DRMS principle is an extended version of Newton's second law, which is used to solve problems on dynamic equilibrium where the body is subject to dynamic equilibrium. So, because that acceleration term is there, we have to stick on to that the body is moving. So, for solving problems on DRMS principle, what we have to do is dynamic equilibrium equation, that is vector minus m into vector A is equal to 0 is written along the direction of motion and the unknown is outside. So, we should write this equation and whatever unknown is there, that we can find out. Suppose if there are two unknowns, one unknown is there, one equation is available, you can solve. Suppose if there are two unknowns in the given problem, then you have to use this second equation also. So that means one equation along the direction of motion of the body, another equation perpendicular to the direction of motion of the body. So you can have inclined plane also. Suppose if a body is moving on an inclined plane, then if this is the direction of motion, then we can write one equation along the direction of motion. So it is like this: P is the force, W is the weight of the body, and inertia force will be acting in the opposite direction. This is direction of motion. Inertia force, which is nothing but Fi, which is m into A, which acts in the opposite direction of the body, where m is given by W by G. W is the weight of the object, which is given. So we are going to write equilibrium equation, dynamic equilibrium equation along x-axis, which is parallel to the plane, as well as along y-axis, which is perpendicular to the plane. Of course, if this inclined plane is rough surface, then frictional force also will be there like this, normal reaction will be there like this, and frictional force is given by mu times L. So these are the things you have to keep it in mind to solve a problem on dynamic equilibrium equation. That means in general we can say that DRMS principle is used to solve the problems on dynamic equilibrium.